In this lesson, we're going to look at linear programming. So in our previous lessons, we learned how to create an algebraic model. That's our step one here. That includes a defining statement of variables used in your model, the restrictions on the variables, a system of linear inequalities that describe the constraints, and we also learned how to create the objective function that shows how the variables are related to the quantity to be optimized. Okay? Now, if I go up here, the solution to an optimization problem is usually found at one of the vertices or corner points of the feasible region. And that's the part that you're stippling or you're shading. So it's those corner points. One of those corner points is the solution. And to determine the optimal solution to an optimization problem, we are going to plug those into our objective function. Okay? Step 2, we're going to graph the system of inequalities to determine the coordinates of the vertices of its feasible region. Step 3, evaluate the objective function by substituting the values of the coordinates of each vertex. Step 4, compare the results and choose the desired solution. Step 5, verify that the solution satisfies the constraints of the problem situation. So let's take a look at example 1. In example 1, we're going to revisit a question that we've done previously. So if you flip back to page 13 in your notes booklet, we did this example about creating a model with the two toy cars. One's a racing car, one's a SUV. And we went through and we got all of our restrictions and we got our constraints and we got our system, and then we went ahead and we graphed it. We stippled the feasible region, and remember we were talking about these 3 corner points there, right? So those corner points are the corner points of our feasible region, and we're going to use those now, right? We talked about our our objective function here, 8x plus 12y is equal to the cost. Then we plugged in those corner points to figure out what costs the most, which combination of SUVs and racing cars cost the most, and which costs the least. So if we go back here to page 17, we can reread the question. It says a toy company manufactures 2 types of toy vehicles, racing cars and SUVs. Because the supply of materials is limited, no more than 40 racing cars and 60 SUVs can be made each day. Same problem. The company can make 70 or more vehicles in total each day. It costs $8 to make a racing car, $12 to make an SUV. So, because there's so many different combinations in that feasible region that could be made, we just want to know which combinations result in the minimum and maximum costs. If we look at the next page, we have a digital version of the graph that we made. Okay? And you can see, I'm going to shade it, but it's not what we need. This triangular part here is that feasible region, right? And you can see our lines even have dots on them because not everything along those lines, I'm referring to these lines here, not everything on those lines are possible solutions. It's only the ones that occur at the crosshairs, right? So this green dot, for example, is the only solution because it's discrete. We can't get values in between. Okay, now on your graphs, you guys are drawing the straight lines, and I understand that. As long as you're stippling the feasible region, I'm okay with that. In this problem, they used S to represent sport utility vehicles and R represent the number of racing cars. We used X and Y. It doesn't matter what variables you use. And they labeled our lines on our graph as well. So looking here, our restrictions written a little bit different than what we're used to as well. What does this mean? So S belongs to the whole number set and R belongs to the whole number set. In other words, our variables are going to be whole numbers and our data is discrete. Down here are our restrictions. S is greater than or equal to 0, which makes sense. You can only have positive values for SUVs. R is greater than or equal to 0. You can only have positive number of racing cars. R is less than or equal to 40. So when we're looking at our racing cars, you can't have more than 40, and S is less than or equal to 60, you can't have more than 60 cars. The total number of cars has to be, we would like it to be, greater than or equal to 70. Okay, now our objective function to optimize, our cost is equal to 12S plus 8R. The 12, if you look up here, on the previous page, the 12 is the $12 to make the SUVs, and the 8 comes from the $8 to make the racing car. That's where we're getting our cost. Now, what do we do here? Well, we want to plug in these three values into our objective function and optimize it, our maximum cost and our minimum cost. So if we plug in 3040 here as our first one, you can see up here R is the 40 and S is your 30. Okay, so let's plug that in. C is equal to 12 times 30 plus 80 times 40. So C is equal to 360 plus 320 to give us a cost of $680. Now go ahead and do this for 60, 40, and 6010. Once you've done that, you should see that you get values of 1040 and 800. So now what you're going to do is you're going to look and compare these three values. Those three values represent the costs at those corner points. So in order to maximize and minimize, what you're looking for is the largest value and the smallest value. So 1040, that would give us the maximum cost, and 680 here would give us the minimum cost. And at the end, you're probably going to want to write some sort of sentence. So what gives us the minimum cost? 30 SUVs and 40 racing cars. What gives us the maximum cost? 60 SUVs and 40 racing cars. Let's take a look at example 2. Creating a model for an optimization problem and solving the problem. So we're going to do this all the way through. This would be creating the model, finding the objective function, and then optimizing by plugging in those four corner points. L&G Construction is competing for a contract to build a fence. The fence will be no longer than 1,800 inches and will consist of narrow boards that are 6 inches, wide boards that are 8 inches. There must be no fewer than 100 wide boards and no more than 80 narrow boards. The narrow boards cost $3.56 each. The wide boards cost $4.36 each. Determine the maximum and minimum costs for the lumber to build the fence. Now, a lot of students have a difficult time just at the very beginning figuring out what exactly it is that you need to set up for your variables. And my answer to that is always ask yourself, what is it that we're counting? What is it that is actually variable? What's changing? So here, what are we trying to figure out? Well, we're trying to maximize and minimize the cost, but it's the cost for the lumber. And what we're counting here is the number of wide boards and the number of narrow boards. Let's let X be equal to the number of narrow boards and Y be equal to the number of wide boards, because that's what I'm counting. Okay, Now, what are our restrictions? That's the next thing you're going to look at. And we look at how are we counting. That's what we're referring to when we're talking about restrictions. We know what we are counting, the narrow boards and the wide boards. That's defining our variables. Now the restrictions, how are we counting? Well, we're counting whole number boards. We're not counting portions of boards. So x and y must be whole numbers. The solution set is discrete. Next, we have to evaluate the constraints. And the constraints referred to our inequalities themselves. Now, because we know that x and y are whole numbers, we know that our narrow boards and our wide boards are always going to be positive. That's why we graph in the first quadrant. Now, we haven't been listing these as constraints. We should start now, because even though we always graph in this top quadrant, right, meaning that everything's going to be greater than x and greater than y, we should still list them as known constraints. Okay? What else do we know? We also know from the information they gave us here that there must be no fewer than 100 wide boards and no more than 80 narrow boards. So how would we rate that? Greater than or equal to 100 for our wide boards and less than or equal to 80 for the narrow boards. Now there's one other piece of information they're giving us. At the top here, this first bullet, it says the fence will be no longer than 800 inches and will consist of narrow boards that are 6 inches wide, wide boards that are 8 inches wide. So what does that look like? 6 times x plus 8 times y, and then that would be less than or equal to those 1800 inches. Okay, so we've got our variables defined, we've got our restrictions stated, we've got our constraints. Next, we need to graph this, okay? If you want, you could do your objective function right away. I usually like to graph it first. I'm going to let you hit pause on the video, use your graphing calculator, graph it. You've got lots of experience doing that. Rearrange your inequalities and then press play and it'll show up here. Okay, I'm not going to go through step by step in your graphing calculator. If you're having trouble with that, make sure you come in and see me and we can go over that together. But we've had lots of practice with that. The only tricky thing again is your window, and your y-intercept will help you with that window. So go ahead and graph that and then press play and you can see it here. Once you're done that, then we'll write out the objective function and test that feasible region, those corner points of that feasible region. Alright, so now that we have that graphed, you can see I've labeled all of my inequalities. I've also labeled my x-intercepts, my y-intercepts. The only thing I haven't done here was stipple my feasible region, so you can see where that would be. So if we're looking at 1 and 2, constraints 1 and 2 just tell us that we're graphing in this quadrant. 3 less than my vertical line here would be referring to everything in here, right? If we're going to be doing greater than my horizontal line, that would be everything above here. And then less than my diagonal line would be everything over here. So all three of those overlap, and you can see where that region would be. I'm just going to circle it here. It would be right here. Okay, so that's where we're stippling. I'm going to get rid of all this so we can do that. And go ahead and stipple in that region. Alright, at this point, now we're ready to deal with our objective function. So if we look back up here, this bullet here tells us narrow boards cost $3.56 each, wide boards cost $4.36 each, and then we're to determine the maximum and minimum costs. So our objective function, let's write it out here, would look like this. we would have 3.56 or $3.56 times x plus $4.36 times y, and that would be equal to c. And if you want, when we're defining our variables over here, you can let c be equal to the cost. So you're defining that variable as well. Okay, so what are the corner points of our feasible region? We can highlight them. We've got 225, we've got 100, we've got 8165, and we've got 8100. Those are our corner points. Those are of our feasible region. Now, when you're looking at y-intercepts, don't forget that that's an x value of 0 and a y value of 225. So let's test those points. If we do that one, that would be 0, 225, like I just said. And if we put that in, the cost would be 3.56 times 0 plus 4.36 times 225. Put that into your calculator and you would get a cost of $981.00. Okay? I'd like you to go ahead and try the other 3 corner points and then come back and check to make sure you get the same answers I get. Okay, so at this point you've got your 4 answers and now you just have to evaluate them. Which one gives us the minimum cost? Which one gives us the maximum cost? Having a look at our values, we could see that the minimum cost would use 0 narrow boards and 100 wide boards. Gives us a cost of $436. Maximum cost would use 80 narrow boards and 165 wide boards. And that gives us a cost of, where's that one? Here, $1,004.20. Just be sure that you write some sort of concluding statement at the end. Highlighting those or circling those 2 values isn't enough because we want to see and communicate to whoever's looking at the problem that you've done that those are the solutions that you came up with for the minimum cost and the maximum cost. Thanks for joining me today.